We are dealing with the knowledge area, electricity and magnetism. Now I want to draw your attention to the data sheet. So if we look at the data sheet, there are a few things you need to remember. Right, since we're dealing with the knowledge area, electricity and magnetism, you have the formula for these sections. Right. Magnetism, we dealt with magnetism. There's no formula for magnetism in grade 10. But in grade 11 and grade 12, you will get formula for it. At the grade 10 level, we dealt with magnetism in a qualitative way. And you know that we have field lines. And those field lines and how dense they are gives us an indication of its force. And we will deal with that when you are in grade 11 and 12. But in grade 10, you don't have the formula for magnetism related concepts. Then we have electrostatics, which we dealt with, and electrical circuits. Right, now it's important to know all the formula that's related to a section. Right? So you need to be aware of what formulas are on your data sheet prior to the exam. You also need to know the context, when the formula can be applied, right? And if you know when the formula can be applied, then that means your understanding is a bit more advanced in a sense, because if you know the limits within which that formula can be applied, that means you're understanding the underlying or related concepts related to that formula. And you also need to know what each symbol stands for, right, or represents. So you need to know how and when to apply the formula. That's important. Right. Say, for example, if I look at N, N is a symbol for the number of electrons in electrostatics. We know that, right? But N is the amount of substance, and it deals with the mole in chemistry. So you need to know what N stands for and in what context it is being used. Be aware of which formula is not given. It's also important. Sometimes what happens, if it's a statement of a definition or a law, it is not given. Sometimes you have Newton's first law, and because it's a definition, you find that that particular formula is not may not be given. Right, now here we have a data sheet, and we have our section electrostatics, which we have there, and we essentially have two formulas. The one has to do with N is equal to Q upon E, and we know N stands for the number of electrons, right? Q is a charge on that object and E is the charge on the electron. Right, if we look at this one here, you find that Q is equal to Q1 plus Q2 upon 2. Under what situations do we use that formula? If you have two spherical objects and they are charged, and when they charge and they brought together and then separated, and we want to determine the charge on each sphere, then we use this particular formula, right, for that situation. If the charges are not spherical and the shapes are not the same, we cannot just use this formula. We may use it to approximate what the charge would be after distribution, but as long as you know the limits under which this particular formula can be used, that's an important aspect of learning the context of a particular formula. Then we also have Q is equal to IT. Under what conditions can you use it? You can see I is equal to Q is equal to I times change in time, right? Normally, sometimes when I write it, I just write it as Q is equal to IT instead of changing T, because I take the initial time as being at time 0. And then we have this formula here. You know, it applies to parallel circuits, and when you see that, you know that applies to a series circuit. So you need to know this. And we also have V is equal to W upon Q, which means work is the work done by a battery, or it could be work done in a component. So you need to know what that formula stands for. And Q is the charge which is moved when work is being done. Once you know the context, and then you can relate the formula to that. Right. Okay, so now let's look at the first one. In here, what I have essentially done is I have given you like 3 very similar questions in a sense, and all of them deal with at least using 3 ohms and 7 ohms. And in this question, it is these resistors are connected in series. In the next question, it will be connected in parallel, right? And then in a third question, I add an additional resistor to these resistors. The reason for doing that is I just want you to have a sense of how the currents related in the respective circuits, how the voltages are related in the respective circuits, how much work is being done by the battery in the respective circuits. So once you have a sense of that, it gives you an indication of perhaps where is this battery working harder. Is it when the resistors are connected in series, or is it when they connected in parallel? So let's look at the first one we have here. We're going to look at 2 resistors, okay, and they are connected in series, and we have a 21 volt battery. So in all 3 cases, I have left the voltage of the battery to be 21 volts, right? So kept it as a constant. So we want to calculate the total resistance. Okay, if we want to calculate the total resistance, then we say, okay, A, right? We got R total is equal to, let's say, okay, perhaps maybe we just need to draw this diagram. I think that would be easier. Okay, so let's say we have now a voltage of 21 volts. Okay, then we have a 3 ohm resistor, and we have a 7 ohm resistor. Okay, I've made 7 ohm resistor slightly longer. Okay, and then we can have a voltmeter here, right, across that resistor, and we can have a voltmeter here across that resistor, right? Voltmeter here, right? So we got a voltmeter here and a voltmeter there, and we could call this the voltmeter across the 3 ohm resistor, and this is the voltmeter across the 7 ohm resistor. Okay. So let's just do that nicely. We say we have a voltmeter here. So this voltmeter is a voltmeter. We could have called it V1 and V2, but I sort of prefer doing that, so I keep track of what I'm doing. So here, and we have a voltmeter here, and say that's a voltmeter across a 7 ohm resistor. Okay, now we say what is the total resistance, right? We say, so let's call this maybe R1 and R2. Okay, so if I had labeled it R1 and R2, then I could have said V1 and V2. Alright, but let's continue. R right, we're saying R total is equal to R1 plus R2, which is then equal to 3 ohms plus 7 ohms, which then gives us 10 ohms. Right, so the total resistance of this particular circuit is 10 ohms. That means if I have to have an equivalent resistor for 3 and 7, I could then substitute one 10 ohm resistor in this particular circuit, and it will have the same resistance as the 3 ohm and the 7 ohms. So there you have that. Right, now we want to know what is the current in the circuit. So let's say B, the current in the circuit, we say, okay, I total, it means we want the total current in the circuit, and we know we got total voltage, right? The total voltage is the voltage that the cell has and applies to the external circuit. And then we have R total, which we then say, okay, this is equal to V total, we know is 21 volts. R total is 10 ohms. So therefore, the current or the total current in the circuit is equal to 2.1 amps. Right? There's a total current in the circuit, and this is a series circuit. Being a series circuit, we know that the current is the same throughout, right? So our current in the circuit is equal to 2.1 amps. If we decide to put our ammeter here, it is also reads 2.1 amps. Right? Even if I have it in between these resistors, it's also going to read 2.1 amps. Right? It's the current in the entire circuit. Okay, then if we look at the next one, C. Right? Let's see what C asks for. It says calculate the voltage across the 7 and 3 ohm resistor. So we want the voltage across the 7. We want the voltage across the 7 ohm resistor, and we want it across the 3 ohm resistor. What we know is that the voltage across the 3 ohm and the 7 ohm must add up to give us 21 volts, since resistors in series are potential dividers, right? They divide the potential of that particular battery. So if we want to now have the voltage, so we say, okay, voltage across the 7 ohm resistor is equal to, we need to know what's the current in the 7 ohm resistor. So it would mean I in the 7 ohm resistor times the resistance of the 7 ohm resistor, right? Which would mean that that is equal, what is the current in the 7 ohm resistor is the same current that's in the circuit, which is 2.1 amps times what resistor is a 7 ohm resistor? It's a 7 ohm resistor. So see why I do that. It's a 7 ohm resistor. And what does that give us? It gives us a voltage of 14.7 volts across the 7 ohm resistor. Right, we want the voltage across the 3 ohm resistor. That would mean the current across the 3 ohm, right? Since we're dealing with this, a 3 ohm resistor, we need all information related to the 3 ohm. So we know in the 3 ohm resistor, the current is still 2.1 amps, and then R of the 3 ohm resistor, which would be 2.1 amps times 3 ohm resistor, which gives us 6.3 volts. Right, and as you know, 14.7 plus 6.3 is going to be 21 volts, because now what would the total volts be there across? You just to check that. So V total would be V across 7 ohm resistor plus V across the 3 ohm resistor, which would be 14.7 volts plus 6.3 volts, which gives us 21 volts, which is a total voltage, and we know that that is actually the voltage across a battery. Right. Okay. So we have dealt with that. Now we want to calculate the work done by the battery when the current in the circuit passes the 3 ohm resistor and the 7 ohm resistor, but and in 1 minute, right? So if we look at that, D, we find that we know V is equal to W upon Q, correct? And let's say we want to know what is the work done in the let's say 3 ohm 3 ohm resistor. Okay, say we want to know the work done in the 3 ohm resistor, so we want the work in the 3 ohm resistor. So what is the work in the 3 ohm resistor? We know that W in the 3 ohm resistor is equal to V across the 3 ohm resistor times Q, right? Which is that. But we know that we know that Q is equal to I times change in T, but I said I'll just use T, okay? So if we look at this here now, it means W in the 3 ohm resistor would be the voltage across there is 6.3 volts. We know the current. Okay, so what I'm doing here, okay, let's just get back here, perhaps that would be easier. So let's say, so what I do is I say W in the 3 ohm resistor, is equal to V I T, right? Because I substitute that, and Q is equal to IT, so I have VIT, okay? Which means, and here we have our 3 ohm resistor, and we've got our current in the circuit moving through, so we have 6.3 volts times the current is 2.1 amps times 1 minute, so it's 60 seconds, which gives us, we multiply that out, you get 793 times 0.8 joules. So that is the amount of work that is done in the 3 ohm resistor by the battery. Right, and if we look at the work done in the 7 ohm resistor, okay, which would be equal to VIT in the 7 ohm, okay, so 7 ohm resistor there again, we know that the voltage across the 7 ohm is 14.7 volts. What do we know? We know that the current is still 2.1 amps, and it is for 1 minute, so which is 60 seconds. Okay, when we multiply that out, we get 185 at 185 2.2 joules. Right, and the unit is joules because, say, if we look at this here, right, if I take this like that, we know a volt is equal to a joules per coulomb, and we know I is a coulomb per second, and times a second, which means that cancels out, that cancels out, that cancels out, that cancels out, and then we get joules. Okay, it's useful to do what I call a dimensional analysis, right? So although there we deal with length, but you need to know what the units are, so at least you also know whether the formula you're using is correct. Okay, so we have that, then, okay, we now have what is the work done by the battery when the current in the circuit passes through the 3 ohm and 7 ohm resistor, right? It is the work done by the battery in these respective resistors. Now let's look here. What is the work done by the battery, right? We know what work it has done in the respective resistors. So surely the work that is done in the respect of resistors will then be equal to, right? Say E, we say E Okay, so the work done by the battery is equal to the work done in the 3 ohm resistor plus the work done in the 7 ohm resistor, which means we have, right, 7, 9, 3.8 joules plus 185 2.2 joules, and if we add that up, that gives us 2646 joules of work that was done on these two components or elements. That means the battery is actually losing that amount of energy per unit time. So it does that. It loses that amount of energy because it transfers energy to these components. But let's just double check this and verify it. So let's say alternate. You look at it alternately. Alternate way of looking at it. We know how much is supplied to these components, but let's look at, for instance, the battery, and we know W of battery, or there's a total work it's doing, is equal to V, right, of the battery times the current in the circuit, which is the total current, right, times the time, which is times the time, right, which is VIT. So here we got total voltage is 21 volts times the current in the circuit we know is 2.1 amps times the time we're looking at is 60 seconds, and when we multiply that, what do we get? 2646 joules, which then concurs. Okay, so that's the amount of work it did, and we find that the battery transferred that amount of energy to these uh, components, right? 2646 joules. Right, so you need to realize that the battery supplies the energy, and in doing that, the energy within the battery uh, uh, gets transferred to the components that are external to that battery system. And because it gets transferred, its electrical potential energy in a battery decreases. So how does it replenish that energy? The reactions or the chemical reactions within the battery have to then supply that lost energy, right? And those are things you'll study in grade 12 when you deal with electrochemical cells. Right, then we have here, okay, what is the charge in coulombs that is supplied to the battery in 1 minute, and then it asks how many positive charges of conventional current leave the battery in 1 minute. Okay. Right? Okay, now we have F Okay, so the battery we know supplies 2.1. So the battery supplies 2.1 amp. Correct. So if the battery supplies 2.1 amps, we need to know how much charge is being supplied. And we're looking at a conventional current. See? Conventional current, which means we are saying the charges move from the positive terminal to the negative terminal, and we assume we say that the positive charges are moving, right? So we know that I is equal to Q upon T, which our user symbol implies, which means Q is equal to I times T, which then means that if we look at the current, it's 2.1 amps, right? And for 60 seconds, that would mean it gives 216 coulombs. And since we saying that the positive charges are moving, so let's just say positive 216 coulombs, right? Okay, now we want to know how many positive charges are leaving this particular battery in a second, right? So we know that E, we got F, G, we know N is equal to Q upon E. That was on your data sheet, right? And that E stands for electrons, and Q stood for the overall charge, and N is the number of electrons. But since we're dealing with positive charges here, the positive and negative charges in terms of the magnitude of the charge is the same. It's just that the sign is different when we're dealing with electrons. It is 1.6 times 10 to the minus 19 coulombs negative, and the other one is positive 1.6 times 10 to the minus 19. So if we look at this here now, which means it will be equal to plus 216 coulombs, right? It's equal to plus 216 coulombs all upon 1.6 times 10 to the minus 19 10 to the minus 19 coulombs, but we are now looking at it as for the plus charge. So I'll just write it Q plus to denote that it's a plus charges that are moving. And since we're talking of that, that's that, which then gives us it's equal to 7.825, right, times 10 to the 20 uh, positive charge is moving. 10 to the 20, right? Positive charges moving, and they move from the positive terminal and they go towards the negative terminal. So we can say that, and which is actually positive charges moving. Right? Had we dealt with electron current, that would mean that the amount of electrons that are leaving the negative terminal of the battery. Right? So that gives you an indication of how many charges are moving from the positive terminal and going through the circuit. So it is in terms of charges, it's a lot of charges moving through that at the positive terminal, but that's equivalent to only 216 coulombs. Right, so if you look at it, essentially like from a systems perspective. So from a systems perspective, say for instance, what I'm saying here is you got this battery. Right, there's your battery. Okay. And this battery has its 21 volts and everything, and there's chemical reactions happening. And then you got your 3 ohm component here, and you got your 4 ohm your 7 ohm component there. So what happened? This battery transfers energy, right? And how does it transfer the energy? By doing work on the 3 ohm and the 7 ohm resistor. So when it transfers energy here, it loses that particular energy in the battery, right? And the 3 ohm gains that energy, and the 7 ohm gains that energy. That is why we say at every element in the circuit there is a potential drop. In a series circuit there is a potential drop, right? So some of its potential energy of the battery is dropped at the 3 ohm and the 7 ohm resistor. And when that's dropped, that means the energy in the battery is less. And if the energy is in electric potential energy in the battery is less, the chemical reactions in the battery have to work harder in order to change the chemical potential energy of those reactants and transform them into electric potential energy. Right, now let's look at the next one. Here we have again the same scenario. It's a 3 ohm and it's a 7 ohm, but this time they are connected in parallel, and we still have a 21 volt. We still have a 21 volt battery. Right, now if we look at this, it says again calculate the total resistance. Okay, we want to calculate the total resistance, and let's say, yeah, okay, we already have a circuit, so let's call that 3, let's call this 3 ohms, let's call that 7 ohms, okay? And we could do the same thing, and let's just see, what did I okay, I've labeled R1 there, the 3 ohms, okay. Okay, so that says R1, we got R1 and we have R2, right? That's R2. And also here now we got a voltmeter across this particular two resistors in parallel, and that voltage remains the same, right? And we know when we've got two resistors in parallel, or we've got several resistors in parallel, then the voltage across each resistor is the same, and we know that the voltage remains the same, but the current in the branches differ because parallel resistors are current dividers, right? They're not potential dividers. Okay, so if we look at now A, say A, we want A, and we want to know what is R total, right? R total is equal to R1 times R2 upon R1 plus R2. Okay, I'm using that derived formula, which is now equal to, we say, 3 ohms times 7 ohms upon 3 ohms plus 4 ohms, which means it's 21 ohms upon 10 ohms, which means is equal to 2.1 ohm, right? So here you see that your total resistance is 2.1 ohms. So you can compare it with the other one, 3 and 7 ohms. There your total resistance was 10 ohms. Right. Now, if we look at this, we know that if that's our positive, conventional current comes in there, it goes here, then it's going to go there, right? And then some is going to go there because it branches out here. Okay? And then it branches out and then it comes out there and then it goes back to the battery like that. Okay. So now we want to know what is the total current in the circuit. So we say, okay, B, right? B B, okay, here we say I total is equal to total voltage, which is our battery voltage, upon total resistance. Right, which means our total voltage of the battery we know is 21 volts, all upon the total current, ohms is 2.1 ohms, which tells us that this battery current is 10 amps. Wow. Right, comparatively now to that other one, this one, the circuit current is 10 amps. So if I have an ammeter here, it's going to read 10 amps. And if I have it there, right, an ammeter here, it's going to read 10 amps. But when it comes here to our resistors and it branches off, we want to know, for instance, how much of current goes through there and how much of current goes through there. But we do know that if we use the statement of the law of conservation of charge, that the current in R1 and R2, when they add up, it should give us 10 amps. Correct? Right. So we've got that, and now what's our next question? Our next question says, what is the voltage across the 7 ohm and 3 ohm resistor, right? So we know the voltage across the 7 and the 10 is like the voltage across a parallel branch, and the voltage across a parallel branch is 21 volts. Right, so across the 3 ohm and 7 ohm, it is 21 volts. Right, since 3 ohm and 7 ohm are connected in parallel. Okay, so we know that what the voltage is across that those resistors. Right, but now we want to know what is the current in the 3 ohm resistor. So we say, okay, I across the 3 ohm is equal to the voltage across the 3 ohm resistor and the resistance of the 3 ohm resistor, which means we know the voltage across the 3 ohm resistor is 21 volts because there's the voltage of the battery, right? And upon 3 ohms, which tells us it is 7 amps in the 3 ohm resistor. We know the other one is the resistance is higher. Okay, so I in the 7 ohms is equal to V across the 7 ohms and the resistance of the 7 ohms, which would mean 21 volts, right? Which would mean 21 volts upon 7 ohms, which gives us 3 amps. So that's how that particular current gets divided. Okay, and it gives us 10 amps. Right, so we know what amps we have. Alright, so there we had what is the current in the 3 ohm and 7 ohm resistor. Now it says calculate the work done by the battery when the current in the circuit passes the 3 ohm and the 7 ohm resistor in 1 minute. Okay, so if we go there again, so we want to know what work done. So we know that W, right, in the 3 ohm resistor is equal to V of the 3 ohm resistor times I in the 3 ohm resistor times, okay, so times, let's see, I see times, times the time, which would mean we've got the voltage across the 3 ohm resistor is 21 volts. And what's the current in the 3 ohm resistor? It's 7 amps, right, as indicated there. And what's the time we're looking at? 60 seconds, which is equal to 1 minute. So what's the work done? The work done in a 3 ohm resistor is 8, right, 20 joules. That is the amount of work that is being done by the battery on the 3 ohm resistor. Right, now we want to know what is the work done on in the 7 ohm. 7 ohm in the 7 ohm resistor, which is equal to V of the 7 ohm times I, the current in the 7 ohm, times T. Okay, I've multiplied that now, which means here again, because in parallel is 21 volts, we know that our current here is 3 amps, right, as you can see there, here, and our time is 60 seconds, which would mean in this case the energy or the work done by the battery is equal to 3780 joules. Right. So the battery does this work on in the respective resistors. Right. So, but let's say we want to now know what is the work done by the battery. We know if we look at it from the elements how much work was done there, but let's look at it right. So if we first say, all right, let's say F, okay, the work done, let's say the work, right, total work done, or the work done which is the same as the work done by the battery is the same as the total work done. Okay, let's just do this a bit better. Work done by the battery, right, is equal to the same as saying the total work done by that circuit, okay, which would mean it's equal to work done on the 3 ohm resistor plus the work done by the work done at the 7 ohm resistor, right? Okay, right, which means if we look at this would say as a 3 ohm resistor we have 8820 joules, plus in the 7 ohm resistor it is 37, right, 80 joules, and that gives us 12,600 joules. Wow, look at that, how hard this battery is working as compared to a series circuit. Here the energy that's being transferred by that battery and the charges moving from that particular positive terminal, right, is much more than that of a series circuit. So 12,600 joules are actually being transferred from that particular terminal of the battery. So that is the amount of work done. Remember, the energy can be transferred by doing work, or it can be transferred by other modes of delivery. But here, the energy is being transferred by doing work on these components. Okay? But if we just want to double check this alternatively, we know how much is in each component. So let's just look at it from the perspective of the battery. Alternatively, okay, we could say W, that the battery does work, and that is given by V of the battery, or V total, and I is the current in the circuit times T. So there we got 21 volts, and our current in the circuit we know is 10 amps. And then the time is 60 seconds. And if we look at that, that gives us 12,600 joules. Okay, which gives you an indication of the law of conservation of energy, which you're going to be dealing with in a subsequent section, right? When you're going to be dealing with gravitational potential energy, kinetic energies, but here I'm already talking about the law of conservation of energy. Right, so we have that, and so now we know it's 12,600 joules that's being delivered compared to what was given by here in the series circuit, as you can see there, right? They see how much energy was being supplied by the battery there. Okay, compared to this one here is 12,600 joules, and there's 2646. That means this is roughly about about 5 times more work is being done by this battery, which means essentially that the chemical reactions in the battery are happening at a faster rate, right? Because this is supplying 10 amps to the circuit, whereas the other one was supplying less amps to the circuit. And you see, the thing about this is when you see how much current the battery supplies, you can then determine the rate at which those chemical reactions are taking place in the battery. And that you're going to do like in grade 12. It means the ammeter, or the current in the external circuit, is an indicative measure of the rate of the reactions happening in a particular battery. Right, that's important, but that will be dealt with when you are in grade 12. And the voltage of the cell stayed the same. What has really changed? The voltage remained the same, and of the batteries, but what determines how much current goes into the external circuit? Right, what determines that? Your resistors, whether they connected in parallel, whether they connected in series. How they connected determines what current is flowing in the external circuit. That is why when you have a battery, the battery just gives you an indication of what the voltage is. It doesn't give you a current rating. The current that battery delivers is dependent on what is connected in the external circuit. That's an important point that I'm making, so that you have a conceptual understanding of what I'm saying. Right. And then, if you look at the last one here now, it says which battery is working harder, right? We've already worked it out. The battery in which the two resistors are connected in series, or the same two resistors connected in parallel. So that we know where the battery is working harder. Right, but if we want to look at it a bit differently, we could say G right. G, we could say, okay, we know that W is equal to VIT, right? W of the battery is equal to VIT, and we know that if V is constant, and T is constant, then the work done by the battery is directly proportional to I. Isn't that so? Right. But we know that since I in a parallel circuit is greater than I in a series circuit, right? Which, like I say, that implies, it's the notation I use, which implies that work in a parallel branch is greater than work in a series. Right. Okay. Now let's look at the same two resistors, right? They are connected in parallel, and then we have an additional resistor that has a 0.9 ohm resistance, right? So let's say, for instance, I have that, and we know that's 21 volts. So let's say we have that resistance and that resistance there, and that I've connected it like that, okay? And then this one here is 9 ohms, and here we have 7 ohms, and we have 3 ohms, okay? And let's say I have a voltmeter here, okay? And I could also have a voltmeter there, right? And we know that the voltmeters, this one, so let's maybe call, I'll change the nomenclature, but let's call it A, B, right? Let's call it AB, and let's call this CD. So this would essentially be voltage across AB and voltage across CD, right? So we want to know now, calculate the total resistance of the circuit, right? So the total resistance of the circuit would be V total would be V across, we're dealing with resistance, okay? So we'll be dealing with resistance, then R total would be R across AB plus R across CD. But what is R across AB? We know it's 9 ohms, right? Which means it's 9 ohms. (9 ohms). What is R across CD? We know that we have dealt with. It's 2,1 ohms, which means plus 2,1 ohm, which gives me 3 ohms. So that is the total resistance of this particular circuit. Right. Now, if we want to know, let's say, and we want to know what is the current in the circuit, okay, current in the circuit is equal, we say I total is equal to V total upon R total, which would mean it is equal to 21 volts all upon 3 ohms, which means this circuit has a current of 7 amps. Right, so it has a current of 7 amps, and you could compare the currents in all 3 circuits. Right? Okay. So we want to now calculate the current in a circuit, which we said is 7 amps. Now we want to know what is the voltage across the 3 and 7 7 and 3 ohms, and then we also want to know what is the current in the 3 and 7 ohms. Okay. So we know that now. We need to know what is the voltage. So the voltage we know across the 7 ohms, okay, which is actually the voltage across CD, right? So, which is the same as saying voltage across CD is equal to voltage across that is equal to voltage across the 3 ohms, since they are parallel, right? Since V 3 ohm and V 7 ohm are in parallel. Okay. Now, if we look at RCD, we know across that it was 2.1 ohm. Isn't it so? Right. Now, if we want to know the voltage across CD, so the voltage across CD, that parallel branch, is equal to, we know that it's going to be 7 amps going through that, because that is a circuit current, and the equivalent resistance is 2.1 ohms, which means we have now 14.7 volts across that resistor. Right, so here we have 14.7 volts, and we know 14.7 volts. If we got 21 volts, what's the balance going to be there? It would then obviously be 6.3 volts, which gives us then a total of 21 volts, right? So that's your voltage across that. And what is your voltage across VAB? Like I showed you, that would be equal to 21 volts minus 14.7, which would be 6.3 volts. So now you got the voltage across the respective. Now we want to know what the current is in the 7 ohm resistor. So I in a 7 ohm resistor is equal to V of the 7 ohm resistor upon R of the 7 ohm resistor, which is equal to 14.7 volts, because it's in parallel, across the 7 ohm resistor, which then gives us this 2.1 amp current going through the 7 ohm resistor. Now, if we're looking at I is equal to the 3 ohm resistor, which means V upon the 3 ohm upon R of the 3 ohm, which would then gives us, we know that that we have 14.7 volts because they're connected in parallel, and that's 3 ohms, which now gives us 4.9 amps, and we know that in total that is 7 amps. Right. So if we now want to know what is the work done in the 3 ohm resistor, right? So if you're looking at the work done in the 3 ohm resistor, which means in the 3 ohm resistor, which is equal to V I T, right? The 3 ohm resistor, which is in parallel, we know that it is 14.7 volts, and the current going through that parallel circuit is equal to 4.9 amps, right? The current in CD. Okay, the current in CD. So we just perhaps this, let's do this. Voltage across CD, and then the current in CD, right? Total, and then the time, which then means we have 4.9 times 60 seconds, which gives us 432.8 joules. So that is the energy that's being expended in that particular resistor, right? Okay, and that was in the 3 ohm resistor. So if we want W in the 7 ohm resistor, which is the same, V I T, and that would be we have the same voltage across it, 14.7 volts, and we have the current going through that resistor is 2.1 amps, right? As you can see here, I've given you that 2.1 amps, and times 60 seconds, which then gives me 1852.2 joules. Right, so we know how much is given in the respect of resistors that are in parallel. Okay, so now let's look at F. Okay, so we did that, we got this here. So what is the work done in the 0.9 ohm resistor? Okay, this one here. So in the 0.9 ohm resistor, we say work done in the 0.9 ohm resistor, work done in the 0.9 ohm resistor is again V across the 0.9, right, ohm resistor times I, okay, in the 0.9 ohm resistor times T. But we know that the voltage across this is 6.3 volts, right, because the other one was 14.7. And what's the current? The current in this particular circuit is a 7 amps. It's connected in series times 60 seconds, which then gives us 2646 joules. Right. Okay, and we have now, we want to find out the total work done. It would be work total by the battery is equal to work done 0.9 ohm plus work done by the 7 ohm plus the work done in the 3 ohm, which would mean, right? Which would mean that we have 2, 6, which means 2646 joules plus 1852.2 joules, right? Plus 4321.8 joules, which is then equal to 8820 joules. That means that is the amount of energy that is lost by the battery when the battery does work on these particular components. But just to verify that again, like we did in the other cases, right, which we're going to say W of battery is equal to VIT, and that would be then equal to 21 volts, and we know the current in the circuit is 7 amps, and then we've got 60 seconds, which gives us 8820 joules. It means the battery is doing that amount of work. Okay? Right now, let's look at this one here. Here, we want to calculate the total resistance of a 12 connected in parallel. Okay, so here we have this, there, and we're not given the voltage of the battery, which is fine. There, and we can say this is R1 and that's R2, and this is 2 ohms and this is 8 ohms. Okay, so R total in this case would be R1 times R2 over R1 plus R2, right? Which means R1 times R2 would be 2 times 8 upon 2 plus 8. Isn't it so? And that would then give us 16, okay, 16 upon 10, which is equal to 1.6 ohms. Right. Let's look at the next one. Here we got a 4 ohm resistor. Okay. Then we have a 2 ohm, right? And a 2 ohm and 2 ohm and a 8 ohm resistor, right? And we just did this one here. We just did this. We have here in this situation now, if we want R across a parallel branch, right? So R across a parallel branch would be let's call it, okay, it's R2 times R3, R2 times R3 over R2 plus R3, which is equal to then 2 times 8 upon 10, which is the same as 16 upon 10, which is equal to 1.6 ohms. So what's our total? Our total is equal to our R, which is equal to 4 ohms plus 1.6 ohms, which then gives us R total is equal to 5 ohms. Right, let's look at this one here now. In the diagram below, the ammeters, connecting wires, and battery have all negligible resistance. Right, that's an important aspect. We haven't spoken about that, but the fact that it's negligible resistance, that means there isn't any potential being dropped at this particular at the conductor or even in the ammeter, right? Because remember, an ammeter must have a very, very small resistance, because otherwise current going through the ammeter will obviously, there will be a potential drop. So what's being measured is not the drop across a particular component, because there's a voltage dropped in the instrument as well. So that's an important point, but in most of our cases we assume that the conducting wires and these and the ammeter has a very low resistance, contrary to the voltmeter that has a very high resistance, because it's not really measuring current. The voltmeter is actually measuring the push of the charges. Okay, so here we say when both switches are closed, here, okay, there you got V1. When both switches are closed and the reading on V1 is 24 volts, okay, and the reading on A1 is 0.12 amps, 0.12 amps, and the voltage across the two parallel resistors is 14.4. So if we have a voltage across this, it's 14.4 volts. Okay, if we connected it across, say we connect it across the parallel resistors like that. So that would be the voltage. Say I have my voltage here, voltage across the parallel resistor, so that would be the voltage. So if that's 14.4 volts and the battery supplies 24 volts, then what does the voltage across this, what would it be, right? It would then, we would have a voltage across this, bulb here, right, would be 14.4 plus the sum of the voltage the bulb will then give you 24 volts. So what is a bulb's voltage? The voltage of the bulb is equal to 21 volts, right, minus 14.4 volts, which would mean it will be 6.6 volts. Right, 6.6 volts. So this is going to read here 6.6 volts. Okay. And that would be 6.6 volts. Right now, I say calculate the equivalent resistance of the parallel resistors. Okay, so that's 6.1. We want the equivalent resistance of the parallel resistance, which means 6.2. So if you want R parallel, that would be 300 ohms times 200 ohms all upon 300 ohms plus 200 ohms. Okay, and that would then be equal to that 6 and right, okay, which gives us that all upon 500 ohms. So that cancels out like that, and that would then give us 120 ohms. Right, then let's look at the next one, 6.3. It says, what is the current through the bulb? Right, we know that the current through the bulb here, that bulb is connected in series. So this bulb is connected in series. Okay, the bulb is connected in series. So being connected in series is going to have that same current that the ammeter is reflecting there. Okay, so that means I in the bulb is equal to 0.12 amps. Right, and 6.4, we would like to know how much charge flows through the bulb in 30 minutes. Okay, how much charge moves through the bulb in 30 minutes. So that would mean Q is equal to I times T, which we have now 0.12 amps that goes through the bulb, and 30 minutes we need times 30 times converted to seconds, which gives us that, and that gives us 216 coulombs. Okay, that's 216 coulombs. Now if we look at the next question, 6.5, okay, it's asking us it asks us how much if the reading, right, if the reading on A2 is 48 milliamps, right, this one is showing you 48 milliamps, right, what is the current going through the 200 ohms? So we already know the resistance is lower, so we at least qualitatively expect the answer to be larger than 48 milliamps. Okay, so we say I in the 300 ohms plus I in the 200 ohms I in the 300 ohms plus I in the 200 ohms is equal to I total. So in the 300 ohms, it is 48 milliamps plus I in the 200 ohms. Okay, we don't know, but we know that the total current is 0.12 ohms. So we could just convert that to milliamps and say it's equal to 120 milliamps. Therefore, I 200 is equal to 120 milliamps minus 48 milliamps, and therefore that gives us 72 milliamps, right? As we looked at it qualitatively, and we see that the current is larger there. Okay, there you have it, and see you the next time.